Hey folks, for video 2.4D, I have a change of location for myself, and also we're going to start talking about springs. So I have two videos on springs, one just to introduce the law that describes them, and then a video on problems next. So we're going to talk about Hooke's law for springs, and springs are something that we study in a couple different units. They have some good utility, and the reason why we study springs is because they have a variable force. In other words, a force that depends on some other property of the spring, and in this case, it's displacement. So I have a couple springs here, and ones that we'll use for labs are the ones like this. They have a set length, they're coiled so that all the coils are touching, and then you can only stretch the spring. And when you let go of the spring, one end anyway, it will return to its natural length. So sometimes this is called the unstretched length, sometimes it's called the natural length. This spring, which would be harder to incorporate into a lab without some extra equipment, is the coils are separated a little bit, so you can stretch the spring, but you can also compress the spring, and then when you let go, it will return to its natural length. So springs are things that change length, and as their length is changed, they exert forces. So an unstretched spring has a spring force of 0. It is at its natural length, and so there's no part of it that is under strain or stress, and so it's not going to exert a force to return itself. When you do stretch or compress a spring exerts a restoring force that is proportional to the spring's displacement. So restoring force means that it's a force that functions to return it to its unstretched or uncompressed position. And then proportional to displacement gives us a clue as to the equation. The equation for a spring force is, so F sub S is our variable for spring force. That is equal to negative K times the displacement of the spring. And so that's the official equation in your equation sheet. However, I'm going to ask you to focus only on the magnitude. And so the magnitude of the spring force is just equal to the magnitude of K times delta X. This is the one that I want you to have in your head as you go to do spring problems, because it kind of fits in with the way we've done all the other things in this unit. Okay, so let's talk about these two variables. The first variable is K. K is the force constant of a spring. This is in newtons per meter, and it represents the like stiffness of a spring. So represents spring stiffness. So basically, the higher a force constant, the more difficult it is to change the length of the spring. So a higher value of K means more force required to deform that spring, to either stretch it or compress it. So that's the first variable, K. It is a number. The numbers can be anything. The springs that we use in class have K values of like 8 or 15 or something like that, newtons per meter. So those are really easy to stretch. If you're talking about like the springs in the suspension of your car, then now we're in the like probably tens of thousands of newtons or more per meter. All right, so that's the first variable, and then delta X is the displacement of the spring. So I skipped this picture. I'm going to go back to it now. As I've drawn it, this length right here is what you would refer to as the unstretched or the natural length. And so that's important in our measurements because it's something you would measure before you started to use a spring. If I then pull on one end of the spring, I can increase its length. And so this length here is going to represent the displacement of the spring. So it's not like you're throwing the spring across the room. No, you're stretching it, and you're measuring essentially how far one end of the spring has moved from its unstretched position. And so that would be this measurement here, because the right end of the spring was there, and then it was stretched to that position. So the natural length doesn't end up entering into the equation at all, but it is useful in determining the displacement. And then this negative is super important, because if you stretch a spring, then you are introducing a spring force in the opposite direction. So the restoring force is called that because it always pushes or pulls in the opposite direction that the object is being pushed or pulled. So if I stretch the spring, then the spring force pulls my hand back. If I were to compress the spring, then the spring force is exerted outward. Now, it's a lot like a rope, where there's like a spring force that could happen at either end. And so just remember that when you do a free body diagram, to pay attention to like which object you're diagramming. You're not diagramming the spring, because the spring is going to be attached to something that the spring is either pushing or pulling on. And that's it. So the reason, and the last thing I wanted to talk about is this equation, right? The equation has the negative sign in it because the direction of the spring force is always opposite the direction of the displacement. My last note is use the description or setup to determine the direction of the spring force. Just putting in negative k times delta x is not going to be enough to tell you which way it's pointing. You have to just be aware of what the spring is engaged with, whether it's pushing or pulling on that thing. And so just use k times delta x in your Newton's second law work, and use your free body diagram to tell you which way the spring force is. All right, next video is going to tackle some problems.